Hello and welcome to another presentation, this one on numerical methods. We're going to be looking at trapezium rule. We're also going to be looking at fixed point iteration and interval bisection. Now, I want to start just by talking about what a numerical method really is. We use the term numerical methods for solving problems or equations, if you like, in maths, which cannot be solved analytically. That's the idea of numerical methods, because often it's not surprising really that students assume that mathematicians have an analytical solution for everything. Now, what do I mean by an analytical solution? Well, I mean, for example, if you're given x squared minus x minus 1 equals 0, we have an analytical approach to solving that. What's an analytical approach to solving that? Well, a good one would be just using the formula or completing the square. Let's use the formula. X equals 1 plus or minus the square root of, it's going to be negative 1 squared, which is 1, minus minus 4, so that's going to become plus 4 over 2 times 1. And so we've got an answer to that equation, which is, well, the best way of putting it is it's exact, yeah? It's a square root, so it's actually expressed exactly. Now, that's fine for all quadratic equations, and actually for cubic equations there is a way of solving those using an analytical approach. It's not taught at GCSE or A level. It's not actually even taught very commonly in degree level, I don't think, or at least it wasn't taught to me in my degree level, but there is a method for solving cubic equations. There's a few different ways of doing it, but the cubic equation formula, if you think the quadratic equation formula is complicated, the cubic equation formula is extraordinarily complicated. Now, it's true as well that once you go beyond cubics to the power of 4 and to the power of 5 and to the power of 6, certainly I think by the time you get to quintic equations, we do not have any analytical approaches available to us. Now, it's not just higher order polynomials which don't offer any analytical approaches to solving them. There's lots and lots and lots of kinds of equations in mathematics where we don't have a perfect way of solving it. But we do have the next best thing, which is a non-analytical way of solving it, which is essentially just like trial and error. When you do I think it's called trial and improvement now in GCSE, when you do that, essentially you're guessing at the answer, and you're getting closer and closer and closer to the answer. Well, trial and improvement isn't the only method that we've got for guessing at the answer. We've actually got a few other methods, and we call them numerical methods, essentially. Now, I'll be going into a couple of the more typical numerical methods for solving equations in a second, because actually what I want to start with first is the trapezium rule. Now, the trapezium rule is a numerical method for finding the area under a curve. Now, when I say numerical methods, I want you to think of essentially an imperfect method. It won't find you the perfect answer, but it will find you an answer very, very, very close. That's the kind of things that we're looking at when we're dealing with numerical methods. Okay, so let's start with a formula. The formula is that the area equals h over 2, open bracket, y0 plus yn plus 2 times y1 plus y2 plus dot 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 all the way up to yn minus 1. Now, that formula is actually quite difficult to remember, and that's why I prefer to teach my students a slightly different way of looking at it, or actually it's exactly the same. I'm going to try and interpret that formula for you. The h at the start just stands for strip width. Now, that is the width of each individual trapezia when you're which will always be given in the question when you're trying to find an estimate for the area. So it's strip width over 2, and then I've just put ends plus 2 times middles. And that's because the end y coordinates will go first in the brackets, then you've got a plus 2 times all the other y coordinates in the middle. So let's actually use this formula. Let's say we want to estimate the area under the curve y equals x squared plus 1. Between x equals 0 and x equals 6. Now, when they ask you to do something like this, they'll almost always give you a table. Yeah, they might not, but they almost always do. So let's actually give a little bit more precision as well, because I need to say how many trapeziums I'm using. I'm going to say with 3 trapezia. Okay, so that's what I'm actually going to do. Now, it's not too difficult, this. It really isn't. We just need a little table of values, which is, you know, something which students would have done many, many times, because we tend to use table of values even for just drawing straight lines. So let's actually set up a table of values. So, x and y. Now, if we've got 3 trapezia as well, and we're going from 0 to 6, that means we're going to have to go 0, 2, 4, and 6. Now our y components are going to be easy to work out because we've got an equation up here, y equals x squared plus 1. I'm just going to substitute my x values in, giving me 1, 5, 17, and 37. Now you'll see immediately why I like this formula. It's because I know what the formula means. The strip width is just the width of each x interval, and so it's going to be 2 over 2. My ends are just the end y values, so that's 1 plus 37, the first and last y value. And then we're going to be doing 2 times the middles, which is 5 and 17. And I'll just squeeze it in there. And so we've got 2 divided by 2, which is 1. So I'm just going to ignore that 1 times outside the bracket. So I've actually got 38 plus 2 times 22. And hence I've got my answer, which is 82. And that's an estimate for the area under the curve y equals x squared plus 1 from x equals 0 to x equals 6. Now, I just want to show you what we've done there, just so you really understand what we've tried to do. Essentially, the trapezium rule is a simplification, a simpler way, if you like, of separating the curve into trapezias. We could write this curve as 3 trapezia. And then if you can just do this last one up here, it was almost off the chart, really. There we go. Yeah, separating the area up into 3 trapezia, and then actually working out the areas of those trapezia. Now, if you just draw a sketch like that, we've actually found this area. Now, I hope you can see, as we've found that area, all these little, they look like segments really, all these little segments here, here and here, actually were counted when they shouldn't have been. And so this kind of shaped curve is going to generate an overestimate. If the curve was actually going the other way round, it would generate an underestimate. Let me just show you quickly what I mean. Basically, if it's that way round, if it's concave, you're going to get an overestimate because you get extra bits there than there. But if you think about it, if you had a curve which was shaped like this, and you were breaking it up into trapezia, well, you would definitely get then an underestimate because the trapezia would actually lie beneath the curve, if you see what I mean. So you might get the question asked about whether your answer is an overestimate or an underestimate. Just consider the shape of the curve and you should be able to figure that out. Okay, now let's move on to the other 2 kind of iterative methods which you're going to be required to know for new GCSE specification. Actually, this isn't entirely true because it's a bit of a guess for everyone what exactly the specification means by use iterative methods to solve, to find the roots of equations. The roots of equations, by the way, are simply just the solutions to the equations. Don't ever worry about that word root, it simply means solution. Now, that's all the specification says, and it's quite vague, really. It doesn't mention fixed point iteration, but it does mention iteration. It doesn't mention interval bisection, but interval bisection is an iterative method. So I'm going to show you 2 different possible iterative methods that you might be required to know. We're looking forward to the papers coming out and seeing exactly what the exam boards are going to put in the new GCSE spec. But this is good for you to learn anyway, because it's very similar to the trial and improvement approach. Particularly this one, because you can see exactly how it works. Now, if you're ever solving where equation equals 0, you are finding where it hits the x-axis if you were to graph that function. Because if we've got y equals f of x, and we're trying to find where it hits the x-axis, well, clearly on one side of the x-axis, it's going to be of positive value, and on the other side of the x-axis, the y-coordinate will be of negative value. That's what we're going to use interval bisection for. So the way I'm going to start this is I'm going to say, okay, I know it definitely lies between x equals 2 and x equals 3, and what I'm going to do is I'm going to bisect that interval. Because you may not have seen this notation actually. When I write something in square brackets like that as 2 and 3, I'm saying definitely the value of x which generates y as 0 lies between x equals 2 and x equals 3. Now I can show you that that's definitely the case as well using a method called change of sign. If I plug in x equals 2 into there, if I call this f of x, firstly say f of x is x cubed minus 2x squared minus 1. I can prove to you that definitely the root lies in that interval between x equals 2 and x equals 3, because if I plug in f of 2, I get 8 minus 1, which is negative 1. And if I plug in 3, I get 27 minus 18 minus 1, which is 8. Now the fact that there is a change of sign there, the fact that one of the answers is negative and one of the answers is positive, guarantees that the answer, the value of x for which the whole thing becomes 0, it must lie somewhere between 2 and 3. And so what I've done there is I've shown you, I've guaranteed that x must lie somewhere between 2 and 3. Now let's actually get on with the interval bisection method. Let's try x equals 2.5 because we bisect the interval. Plug in x equals 2.5, and I'm going to quickly do that on my calculator. 2.5 cubed minus 2 times 2.5 squared minus 1, and I get the answer 2.125. Now remember, I'm looking for a change of sign. Now the change of sign here occurs between 2 and 2.5, because when I plug in 2 I get a negative number, when I plug in 2.5 I get a positive number. That means that x, that the root, must lie between 2 and 2.5. And I'm just going to write it down like this. Now, that's just using interval bisection once, and it's asked us to use interval bisection twice. Now we know that x is definitely between 2 and 2.5. By the way, I could write it in square brackets and just write 2, 2.5. But now I know that, I'm going to bisect the interval once again. This time I'm bisecting between 2 and 2.5, and that will be 2.25. And I'm just going to plug it in into my calculator. 2.25 cubed minus 2 times 2.25 squared minus 1. And this time I'm getting 0.265625. Now notice, now I can see that x definitely lies between 2 and 2.25. And so I can say, so 2 is less than x, which is less than 2.25. Can you see how I'm getting closer and closer and closer here to the value of x by halving the interval each time and just looking for that change of sign? That is the interval bisection approach. Half the interval, look for a change of sign. Half the interval, look for a change of sign. It's quite a neat little method, and it is exactly the way you would expect it to work, because naturally you'd have to look for a change of sign to find where the root is for any given equation. Okay, that's interval bisection, and it's not the most efficient approach. Fixed point iteration, which we'll look at now, is a much more efficient approach. So let's have a look at that. Now, this method is quite a technical method. We start off with an equation of the form f of x equals 0, because we're always finding the roots of the equation. And we rearrange that, this into a different function, g of x, which equals x. And that's quite an unusual thing to do, really, because we very rarely make an equation x equals with a function of x on the other side, but you certainly need to in fixed point iteration, because once you've done that, you can then use the iterative formula. And let's actually write it down. X to the n plus 1 equals g of xn. And that is the iterative formula. Now, what does it really mean for something to be iterative? Well, it means you plug in an answer and out pops a better answer. And then you're going to plug in that better answer and out pops an even better answer. Then you're going to plug in that better answer and out pops a better answer. That's what an iterative approach really means, certainly in the context of numerical methods. You'll notice that that's really what happened with interval bisection. We bisected the interval and then we said, it's definitely between 2 and 2.5. Then we bisected the interval again and said, it's definitely between 2 and 2.25. Well, that's an iterative method as well. This fixed point iteration method, though, involves two steps. Firstly, rearrange f of x equals 0 into a different function of x equals x, and then use next answer. Essentially, x to the n plus 1 means next answer equals plug in the last answer into g of x, and then that will kick out another answer and another answer and another answer. Let's actually see it in action, because it's quite hard to understand what it really means when you just see it described like that. Okay, so let's get stuck into this question. It's exactly the same problem as what we were doing with interval bisection, but we're going to see how fixed point iteration is a lot better. A lot quicker, shall we say. Now, we're given that x cubed minus 2x squared minus 1 equals 0. And the first thing it asks us to do is show that this can be rearranged to give x equals 2 plus 1 over x squared. Now, this is your x equals g of x, and they will always give it to the student, for the very important reason that not all rearrangements will necessarily converge on the root. So it's a technical reason where the exam is absolutely forced to give you this rearrangement, and that's why it's a show that question. And that's fine, we can show this straight away. So we've got to rearrange this equation here, the very first equation that we have here, we've got to rearrange it into the equation beneath it, x equals 2 plus 1 over x squared. So let's have a go at that. Okay, I'm going to start with, as I can see, there's a 1 over there, 1 over x squared. What I'm going to do first is I'm going to add the 1 over. Then I think it would be a nice idea to factorise out an x squared on the left-hand side. Now I'm going to divide by x squared. And then lastly, I'm sure you can see where I'm going with this, I'm going to add 2. And lo and behold, I have their rearrangement. Now that's very good. That is essentially half of a fixed point iteration question, and what's more, it's normally the trickier half. The easier bit actually is just using this iterative formula. They always tell you the starting value, once again, so everybody finds exactly the same values as they should do. And all we're going to do, to find x2, we're going to need to plug in x1 as 2. So we get 2 plus 1 over 2 squared. Well, that's a quarter, 2 plus a quarter, and so that's 2.25. We're then going to plug in 2.25 to get x3. 2 plus 1 over 2.25 squared we're going to do now. And if we quickly work that out on a calculator, we get 2.198 to 3 decimal places. Now, let's just quickly work out the very last one on a new page. And if you just plug in the last answer again into this iterative formula, you just plug it in and out pops 2.207. So using the iterative formula really is quite straightforward. It is literally take the first value they give you, plug it in as your x, out pops your next answer. Then plug that answer in, plug it in as your x, out pops your next answer. And these answers should be getting closer and closer and closer to the root. Now I just want to show you something they might say at the end in like a part C of these questions. Sometimes they say things like, show that the root is given by x equals 2.206, because it actually gets closer and closer and closer. If you look at x5, x6, x7, it actually goes towards 2.206. Correct to 3 decimal places. Okay, if we're doing this, what we need to do is look for a change of sign again. That change of sign trick, exactly the same trick we were using in interval bisection, always works. Now, if you remember, our original function was x cubed minus 2x squared minus 1. And you definitely want to use the original function for this kind of problem. What we're going to do is we're going to plug in 2.2055 into that equation. And when you do, if you input the value carefully, you should see it comes to negative 0.0004. Now, I hope you can guess that what we're going to plug in now is the value just on the other side of the root, 2.2065. And when we plug that in, we get 0.00537. And so, as you can see here, we've generated a change of sign. What we've shown basically is, if you look really carefully at the graph, and this is a zoomed in graph, when you plug in 2.2065, you get a positive answer, and so it will be above the x-axis. That's your 0.00537 there. But when you plug in a negative answer, 2.2055, when you plug in 2.2055, you get a negative number popping out there. And that shows that's supposed to be 0.2055 on the left-hand side of the curve there. That is enough to show and enough to conclude. Hence, x equals 2.206 correct to 3 decimal places. And that is all there is to it. So, with these numerical methods, like I say, it's really a bit of a guess really for us exactly how much detail the exam will go into it. These questions have actually been stolen from A-level exam papers. They're A-level style questions, but they're moving into GCSE. And so, yeah, they're not that difficult, to be honest. It's just a routine. You do get used to it. But those are the topics which have now been come out into the new GCSE textbooks, so we can only assume that that's what the smart money is betting on the questions looking like in the exam. Okay, I hope that was useful, and I hope that you're okay with a unit assignment now on numerical methods. Good luck.